Okay, so what I want to do in most of the lecture is sort of take you through a number of sort of methodological approaches to how you can refute arguments persuasively. And some of these are going to work better for a technical audience, some of these may work better for a lay audience, and you want to keep that in mind. But I think all of these are sort of useful to think about. And one of my favorites for any audience, partly because it works so well both for professional statisticians and for your seatmate on the airplane or your in-laws at the Thanksgiving table or whatever it is this approach of reductio ad absurdum. And the whole idea with reductio is you want to show that an argument's methods or assumptions lead to ridiculous conclusions. So say, okay, you argued this using these methods and assumptions, and you got to your conclusion that seemed reasonable, but I can use those same methods and assumptions to get to ridiculous conclusions, and that means your argument is suspect. Let me give you a couple of examples. So this was one of my favorite examples of reductio. This is a paper that was actually published in Nature, top scientific journal, I think in 2004. And what the paper does is it looks at sprint times, the gold medal winning times in the 100 meters, in the 100-meter dash in the Olympics from every 4 years. And they plot out these values for men and for women. And they notice that, wow, we can actually fit these values with a linear regression. And that turns out to be a good way to fit the data since 1900. And then they say, well, if we fit it with a linear regression and then we extrapolate, you'll notice that by 2056, we have a very interesting event where women are now actually running faster than men in the Olympic 100-meter finals. And so that's the content of the paper, and it was published and so on. And there was a flood of responses to this paper. A high school class in Texas did a beautiful job of refuting the fundamental argument here. But the cleanest and clearest and simplest way of addressing this was a gorgeous reductio that I'll show you. So here it is, and I'm going to read it. Sir, Tatum and colleagues calculate that women may outsprint men by the middle of the 22nd century. They omit to mention, however, that, according to their analysis, a far more interesting race should occur in about 2636, when times of less than 0 seconds will be recorded. So it's not necessarily ridiculous that women will be outsprinting men at some point, but it's obviously ridiculous that there'll be negative times recorded in the Olympic 100-meter dash at any point. And so what this is pointing out is that this model that they're using, taking a linear regression through these points and extrapolating it out hundreds of years or over 100 years is, when you know that a linear model can't be correct for arbitrarily long because it'll take you down below 0, is ridiculous. And so that sort of undermines the entire initial claims in, what is that, 2 sentences, right? And it's a slam dunk. It's beautiful. Any professional statistician will laugh. You can explain it to anyone you meet on the street, they'll laugh. And that's a beautiful way of refuting bullshit. We saw an example of this in our lecture about graphical malfeasance. So here, if you remember, is what I'm picking on the National Review today. I don't mean to do that. What the National Review called the one climate change graph, the only climate change graph you need to see. And, the notion is, well, it looks pretty flat to me. And then Bloomberg responded with reductio in graphical form, which was this one. And this is their Parmenides was right sort of argument that time isn't passing because, of course, here they're graphing time against time, and because they've chosen their axes the same way, it looks like time isn't increasing either. So they're saying, if you accept that way of looking at the data, you can get utterly ridiculous conclusions. So that's another nice reductio. My favorite reductio, though, is a little bit more elaborate. And this is an attack on the the sort of uncareful use of fMRI studies. fMRI is a way of visualizing neuronal activity inside the brain of a living person or other organism by using a technique that essentially quantifies the amount of blood oxygenation and thus the amount of blood flow in a specific region. And so, you look at a picture like this. In this case, we've got these regions are regions that behave differently in the brains of schizophrenics versus the brains of normal people when doing a memory task. And so the idea is, well, this must be saying something about why schizophrenics are different. They're using a different part of their brain for this task. The problem is is that these algorithms often have a huge number of false positives. And there's been a lot of sort of technical arguments written about this. And in fact, there was an interesting example of things going wrong in science. There's actually a bug in the code that caused people to report much higher confidence values for years than they actually deserved. That was discovered last year. So everyone sort of had this sense. But anyway, these often generate these false positives. Now you want to make a really convincing case of that maybe even allows you to convince a layperson as well as a scientist without getting into p-values and Bonferroni corrections and all of this. And so how do you do that? So I guess the consequence of this, of course, is that a lot of these claims that are being made about regions of brain activity may be bullshit. And so you want to make this argument. And how do you do it? Well, you start with a dead salmon, or at least that's what these guys did. So they went and they got a dead salmon. Because it's fairly clear to a lot of us that dead salmon are not doing a whole lot of complicated cognitive tasks. But the experiment that they did was to put a dead salmon in the scanner. So they say one mature Atlantic salmon participated in the fMRI study. The salmon measured approximately 18 inches long, weighed 3.8 pounds, and was not alive critically at the time of the scanning. It's not known if it was male or female, but we don't think it matters because it was dead, to paraphrase. So they start out with something patently ridiculous. They're going to put a dead salmon in the scanner, see what it's thinking about. And then they do something really, continuing in the sort of humorous reductio. They ask it the same questions that a lot of human psychiatrists or psychologists are doing. They show it these pictures of humans in emotional circumstances. And I know one of the authors, and they actually did ask it. The salmon was then asked to determine which emotion the individual in the photo must have been experiencing. So they really got the pictures. They really did ask the dead salmon to do this, which is delightful. And this dead salmon performed marvelously. In fact, the dead salmon, if you compare neural activity in the salmon when it's distinguishing these human pictures of humans with their emotions versus when it's not, the dead salmon is thinking really hard right there, and then also actually down here in the spinal column, that part of the spinal column is also thinking really, really hard as well. And so what these guys have done with this paper, what these authors have done with this paper, is we'll just put it in their words. Either we've stumbled onto a rather amazing discovery in terms of post-mortem ichthyological cognition, or there's something a bit off with regard to our uncorrected statistical approach. In other words, if this statistical method, if this technical method can find the part of a dead salmon's brain that's thinking hard when trying to distinguish human emotions, then there may be something funny about the method. That's a lovely reductio. What we conclude is that random noise in the time series may yield spurious results if multiple testing is not controlled for. In a functional image volume of 130,000 voxels, these are the little sort of maybe million neuron regions of the brain that you're looking at, the probability of a false discovery is almost certain. You'll almost find some parts that light up when it's not real. So there are many, many arguments have been made about this. A lot of technical statistics written. This one is the one everyone knows. It's a brilliant reductio. It's funny. It's memorable, as we'll get to. And that is, I think, a beautiful example of how you refute something that's largely nonsense.